In this video, I want to talk about carbohydrates. Now, you might be familiar with carbohydrates, and sometimes people just call them sugars. And I want to just give a brief introduction to them. So, the simplest carbohydrates are called monosaccharides. But before I get into that, I want to talk about the sort of formula for carbohydrates. They're carbo, right, implies carbon. Hydrates implies water. So if we think about carbohydrates, they really are just something that is like this: CH2O N, which sort of is anything that has carbons and waters in this sort of ratio. So it'll be CnH2nOn. So an example of this that we're going to talk about later is glucose, which is just C6H12O6. And the simplest carbohydrates are monosaccharides, which is just basically just means one sugar. Monosaccharides. These are the simplest sugars, or simple sugars, that can't be broken down further. And we're going to talk about them specifically in a later video. But I kind of want to introduce carbohydrates as a sort of concept first. When we think about carbohydrates, we normally think about the most basic one being glyceraldehyde, which looks like this. I'm actually going to, so glyceraldehyde looks like this. Oops. Glyceraldehyde looks like this. It has CHO at the top. I'm drawing the Fischer projection at this point. CHOH and then a CH2OH. Now, glyceraldehyde has 3 carbons, and it has an aldehyde group up here. So it is therefore actually specifically an aldotriose. Okay, aldo because it has the most oxidized carbon at the top is an aldehyde, and triose meaning that it's a 3-carbon sugar. 1, 2, 3. Another 3-carbon sugar is dihydroxyacetone. Dihydroxyacetone, which looks like this. Okay, now this is also a triose because it has 3 carbons, but it's a ketotriose, right? The reason it's a keto is because this carbon here is a ketone, right? These hydroxy groups are out here. This is not an aldehyde. This is a ketone because there are carbons on either side of this carbon that's double bonded to the oxygen. So this is a ketotriose. And just in general, you have aldoses and ketoses, and then usually you have either if it's a 3-carbon sugar, it's a triose, and then 4 carbons would be a tetrose, pentose for 5, hexose for 6, and so on and so forth. Really, anything that ends in ose is a sugar of some sort. Okay, ose, sugar, or carb. Okay, so this glyceraldehyde actually has chirality. So if we draw out the Fischer projection, I haven't actually drawn out the Fischer projection, but I'm going to actually right now for glyceraldehyde. Let's do the Fischer projection so that we can discuss chirality. Okay, so you can draw glyceraldehyde, the simplest monosaccharide, like this. Okay, this is specifically D-glyceraldehyde, whereas this is L-glyceraldehyde. Now, all we did was just switch the H and O and the OH. If you remember with Fischer projections, these horizontal lines represent groups that are coming out of the plane towards you, and then the vertical lines are implied to be going backwards into the plane. So, if you recall, D sugars are the ones that we're concerned with when it comes to biology. They're the ones that exist in life forms, whereas the L sugars are not what we think about. L amino acids are in biological organisms, but D sugars are in biological organisms. So these two are related in that they are enantiomers of each other. Okay, these two are enantiomers. Okay, and I want to define enantiomers. Enantiomers are stereoisomers that differ in absolute configuration at all chiral centers. Okay, so these two only have that one chiral center here, and so they differ in absolute configuration there, and hence they are enantiomers because they only have that one chiral center. And again, so most natural sugars are D sugars. Okay. So now I want to talk about. So actually, whenever we draw sugars, we think about the D sugars that have an OH, the OH pointing to the right on the last carbon before the CH2OH. Whoops, I forgot to put the H on that carbon there, or on that CH2OH group. There we go. So when the OH is on the right, that's what we think about when we think about D sugars. Okay, so there are, however, these things called diastereomers, which I'm sure you've heard the term before. What are diastereomers? Diastereomers they are stereoisomers that differ in at least one but not all stereocenters. Differ in absolute configuration, to be specific. Okay, so stereoisomers that differ in absolute configuration and at least one but not all stereocenters. Okay, because if they differed at all the stereocenters, they'd then be enantiomers. Okay, so let me give you a quick examples here. So if we had these 4 carbon sugars here, if we had, for instance, if we had this here. Okay, if we had this is D erythros. Okay, and we know that it's D because the OH group here, the last carbon, right, from the top down, is its OH group's on the right, so it's definitely a D. Okay, so now this here would be OH. This here is L erythros because all of the stereocenters, right, these two here, are exactly the opposite, and so they're actually mirror images of each other, right? So they are enantiomers. Okay, but what about these? Well, these are also 4 carbon molecules, or 4 carbon sugars. This here is D-threose. Okay, notice how it only differs from D-erythros in that it's still a D sugar, right? Because the OH is on the right side. This bottom OH, right? It's on the right side. But here it differs from erythros, right? So this is actually a diastereomer of erythros. Okay, but it has its own mirror image, which looks like this. Right, which is L-threose. Okay, so these two are enantiomers, and these two are enantiomers, but this and this, D-threose and D-erythros and D-threose, are diastereomers, L-erythros and L-threos are also diastereomers. Okay, and keep in mind, when it's on the last OH is on the left side, it's an L sugar. When the last OH is on the right side, then it's a D sugar. Okay, so let's go forth with a further example. Okay, let's think about glucose and galactose because they are very important sugars. So we have, let's draw glucose. Looks like this. It's a 6-carbon sugar, so we have a CHO and then a CH2OH. Those are the 2 carbons, and then in between that we have 1, 2, 3, 4 carbons that have H's and OH's. So glucose looks like this. Okay, this is actually glucose, and specifically it's D-glucose because this last OH is on the right. Okay, now this here, what I'm going to draw is going to be D-galactose. So even if you don't know the structure of galactose, you know that the last carbon on the right is going to have to be an OH. The last carbon has to have the OH on the right, excuse me. Okay, so it actually looks like this. Okay, so now notice here, these two only differ at the 1, 2, 3, 4th carbon, right? Only at the 4th carbon do they differ, right? You start the numbering at the most oxidized carbon, which is that one. So 1, 2, 3, 4, 5, 6. Same thing over here. So these guys are diastereomers, right? Because they differ at least one, but not all of these stereocenters, right? So these guys are diastereomers, but specifically, they are epimers. So let me scroll back up a little bit to mention something. Epimers are a specific class of diastereomers that differ in absolute configuration at only one chiral center. Right? So glucose and galactose are epimers, specifically C4 epimers. Okay? These two. Alright. Now, most of the time when it comes to biochemistry, it's easiest to think about these sugars in actually a different form other than the Fischer projections. What we're going to think about is the Haworth projections, which are circular structures. So glucose and galactose can both exist in linear form, but they can also exist in cyclic forms, which are called Haworth projections. So if we think about glucose, the way it's going to actually cyclize, actually let me draw it over here. So let me sort of title this now as Haworth projections, which is what we're going to get into. Haworth projections are sort of drawn like this. So let's say, again, we have glucose. Let's imagine glucose. We have glucose like this. 1, 2, 3, 4, and then the CH2OH. Let's say we have D-glucose. Let me kind of separate it from this stuff over here. Okay, if we have D-glucose, now what ends up happening is that the way it cyclizes is like this. So if we draw this, we can draw it like this. The ring will begin to form like this. Where here we're going to have the aldehyde, right, the C1 here, group. Okay. Let me actually draw that a little bit differently. Kind of looks like this. Okay. Over here we have an OH group. Specifically, it's this OH group. So let me number these carbons to kind of keep track of them. So C1, 2, 3. Oops, I forgot to draw the hydrogen here. 1, 2, 3, 4, 5, and 6. So carbon number 5's OH, right, the one that we knew determines the D, that's this one here, okay, because this one's going to be 1, this is going to be 2, 3, 4, 5, and then 6 is actually going to come up like this, the CH2OH. Okay, so that's the 6th carbon up there. Okay, so here on the 5th carbon, the OH. So now let me actually draw. Let me finish drawing all of these. So we have the OH group coming down here. The H's are actually implied, so I'm not going to draw all of them. Right? Actually, I'll draw them. Why not, right? But if I don't draw them, it's implied that there's an H there. Okay. So anyways, what happens here is that there are electrons on this OH group here, this one here, right? And they can attack nucleophilically this carbon. Now, they can attack from either the top or the bottom of this. And the reason why is because this carbon is sp2 hybridized. And if you remember, sp2 hybridized means a trigonal planar geometry, right? And if it's a planar structure, then you can attack from the top of the plane or the bottom of the plane. So when this D-glucose cyclizes, okay, this is still D-glucose here, we can form one of two things. Okay, so if it attacks, let's see, we can either get this structure. So all of this stuff, right, 6, 5, 4, 3, 2, all that stuff stays the same. Okay, and again, I'm not going to draw in this case, I'm not going to draw the hydrogens just to save space. But now we're going to have an OH group here. If it attacks from the top of the plane, we get this. Get the OH pointing up. Okay? But if we attack from the bottom of the plane, we get all this stuff is the same. First of all, we get this. Now, the only way these two molecules differ is right here, at this carbon here. This carbon here is the only carbon at which these two differ in stereochemistry. Now, this carbon is called the anomeric carbon. Right? So anomers are a specific type of they are a specific type of epimer, right? Because they differ only at one, and specifically at this carbon, right? This is these two are anomers. This one, in which the OH and the CH2OH on the same side, is the beta anomer. Okay, so this would actually be called specifically beta D-glucose. And this, when the OH is trans to the CH2OH, this one's up and this one's down, right? When they're on opposite sides of the ring, this would be the alpha anomer. Okay? So now these two, the way they're related is these are anomers, which is a specific type of epimer that exists only when these things are drawn in the Hayworth projections, which is this here, right? So once the ring forms, you're either going to have the beta version or the alpha version, the alpha anomer or the beta anomer of the particular sugar. Okay, so that's all I wanted to say in this video. In the next video, we'll be talking about specific monosaccharides and the ones that I think you should be familiar with. Thanks for watching.